Okay, so let's do the seventh problem from the review activity. In this problem, we have particles that are different sizes in part A, B, and C. So we have very small particles in A, somewhat larger particles in B, and the largest particles in C. And what we're wanting to do for these three sizes of particle is calculate the number concentration, how many particles would be present, if we have a mass concentration of 50 micrograms per cubic meter. Then it also gives us the density of the particles, which we're going to need their standard density, which is 1,000 kilograms per cubic meter. Okay, so let's start with B, just because that's the easiest value to handle. In each of these three parts, and we're going to use a relationship that we used earlier in the review activity on the second problem, that the mass concentration divided by the number concentration is the mean mass of our particles. So if we have particles that are monodispersed, meaning they all have the same size, then they should all have the same mass. And so the mean mass is just the mass of any one of those particles. So we take the density of any one of those particles times the volume of any one of those particles if they're spherical. We're given a mass concentration, and we want the number concentration, so then we end up, if we rearrange, with the following. Okay. So we want everything to be in the same units. So I'm going to take our mass concentration and convert it to kilograms per cubic meter. So 50 micrograms per cubic meter equals 50 times 10 to the minus 9 kilograms per cubic meter. So we can use that mass concentration down here. We divide that then by pi, the diameter of our particles, which in B is 1 times 10 to the minus 6 meters, 1 micron, times the standard density. And now if we plug all of those values in, I'm kind of working backwards here from right to left rather than left to right. We get a number concentration of 9.5 times 10 to the 7th per cubic meter. Now, if we kind of cycle around back to part A, right, and we have smaller droplets or particles, right, we should expect that for the same mass concentration, we have a higher number concentration of those particles, right? If they're smaller, we have the same mass concentration, we need more of them to get that mass concentration. So we can use exactly the same equation that we used down here. We'll call this guy star. So we'll do star again up here. The number concentration should be 6 times the mass concentration divided by pi. The diameter of our particles, which is now 0.1 microns, times their density. Right, so you can already see that the only difference between these two is that we have an additional 3 orders of magnitude in the denominator. And so that means we get the same numerical value as part B, just a higher number concentration now, 10 to the 10 particles per cubic centimeter. That checks out with our intuition, right, that we need more particles of a smaller size to get the same mass concentration. And likewise, then for part C, we're going to do exactly the same thing, but we should expect, right, that now if we have even bigger particles, diameter 10 microns, that we should need even less of those to get the same mass concentration. So we plug in our mass concentration, the bigger diameter in the denominator, the same standard density. Plugging all of that in, we get 9.5 times 10 to the 4th particles per cubic centimeter. So we have 3 orders of magnitude, or 3 different orders of magnitude on parts A, B, and C. The smaller our particles are, the more we need of them to get the same mass concentration of 50 micrograms per cubic meter.